practicum. There is a schedule posted on the laboratory door as well as on the class website. I heard a little bit of garblement going on this weekend. This sodium dihydrogen monosodium is a hydrate. And so that means if you dry it and you dry it and you dry it and you dry it and you dry it, you will never get rid of that water. So if you weigh it, you have 1 molecule of water to 1 molecule of sodium and 1 molecule of phosphate. So a hydrate is something that you can't get rid of the water in the crystalline matrix. So if you were trying to get rid of the water in terms of the weight, it's not going to work. So just a little bit of correction. Make sure you give us your sheets at the end of the session, and please come on time. The only one that suffers is you if you come late. Please don't come early, because that will disrupt the people who are actually in the room. There are 3 slots at 3:30. So if somebody wants to come at 1:30 today. So if somebody wants to come at 1:30, see me at the end of class, because there's only 3 openings. So if you wanted to come, just let me know. Okay. Any questions? Everybody's cool? Okay, so it's a short lab today because you only have your part of it. There is a final, and the final will be in this room and in Aubert. And probably the most sensible thing is that we make assignments and say, you come to either this room or you come to the room next to Sue and Jody's office. So I think that will give you a little bit more space for the final. I think it's May 9th at 4 o'clock. So if you have any questions about the final, come next week with them. And this is posted on the website as part of the lecture. So these are some of the topics that will be on the final. So review your quizzes. The quizzes are on the website, what you did in your homeworks and in the lecture. And it will probably take most of you about an hour, so there's a deviation in that. But at least it's the first day of finals, so you'll be done. This is the part of the semester in terms of your reviewing, to really think about what you learned in this module and what you want to keep track of in terms of the final, in terms of other classes. So please, please, please don't walk out of this room and clear the memory bank, because you'll be using this information, this practical hands-on stuff. What's really nice, I got an email from a senior over the weekend, and she said, I want to thank you because this was the first class that I was really introduced to being very careful about my data and how to validate my data. So most of you are probably second-year students, and so here's somebody 2 years down the road saying, looking back, I actually learned a lot, and I learned a lot about being picky and being careful. So as you're going through and reviewing for the final, really, really think about life and what can you take away from this class in terms of really practical stuff. Homework, I think most of you mastered this. This is not the oceanographic convention for depth. The oceanographic convention for depth is 0 is here, and it gets deeper as you go down the y-axis. And some of you were very creative in terms of how to do this, flipping charts and turning things into zeros, but it's really a whole lot easier. So if you click on the y-axis scale and open this dialog box, what you'll see is a little box here that says values in reverse order. So if you check that box, and I think most of you did, you'll get something that looks oceanographically sensible. Why am I always harping on don't connect the dots? don't connect the data points. If you have to have a really good smoothing program, and I'm sorry, Excel doesn't meet that criteria. You know, if you take Dr. Thomas's MATLAB course, you'll learn the statistics and the math behind how you smooth things. And some of you had a data point that, I don't know, it was down here, so you had phosphate looking like this. You know, it looked like it was a roller coaster ride. But unless you have a good smoothing program, don't connect the dots. This is clearly something you're not going to do a regression, right? You know, this is not a regressible type of a relationship. This is Monterey Bay. What do nutrients look like on this particular day as a function of depth? So just be really careful about who's the intelligent one. Somebody sitting in Microsoft programming, or you controlling how your data are going to be displayed. So you got to think about this. Oh, here, this is beautiful. Okay, so the other one is, how do you get the two y-axes? So you add your first parameter, your first variable, and then you add your second. And it might look like this, and then you click on the data point. So you select that second data point, and then you go to the dialog box and select the secondary axes. And then you can have your units for phosphate versus time, and for biomass, for fluorescence, concentration versus time. So I think most of you got that right. So now hopefully everybody's had a chance to work up the data from the experiment. And I guess the big question is, this was the big question that we always have with these experiments. So here's Thalassia syra, Weissflogii. This is what's called the girdle view. So this is the upper frustule. So they have two frustules. They're made of silica. You can see all these little holes in the silica. And so there's, they form nano particles of silica, and then it's laid down on an organic matrix. And in order for a cell divide, what they do is they form this part of what they call the mother cell, forms a brand new frustule inside, and the upper part of the frustule, in order to divide, they form a brand new frustule inside. And then the cell divides. And so they call those the daughter cells. And this is the area that they call the girdle. So the cell divides in two. And that's the reason that we use log base 2. And whenever we do these growth experiments, for the first few days, I'm always like, are they going to grow or not? You know, I know that students often make comments that we're not doing original research. You know, this is a canned experiment. This is not a canned experiment. We're dealing with living organisms, and sometimes the experiment works really well, sometimes nothing grows, and sometimes you wind up scratching your head in terms of the results. So before we look at the data, one of the things I want to do is just remind you, I think it was 2 weeks ago, we talked about chlorophyll fluorescence. And there's living cells, and this is how many? 1, 2, 3, 4, 5, 6, 7, 8. So there's actually 8 diatom cells. It's a diatom called thalassionema. And all the red is associated with chlorophyll fluorescence. And this is similar to what I passed around, an extract of chlorophyll. And so what you actually did was kind of in between. You didn't look at the individual cell with a flow cytometer, which is a fluidic device for separating cells so they go one at a time through a laser beam, and then you can measure the fluorescence as that cell goes through a laser beam. And we didn't extract the chlorophyll, but what we did is we took the culture, put it in a tube like that, and we measured the fluorescence. And what our assumption is that the phytoplankton biomass is proportional to the fluorescence. So that was the underlying assumption for the measurements that you made in the experiment. So you always have assumptions. And next week, we're going to look at fluorescence in the ocean. And I'm suggesting if you want to bring your laptop, bring your laptop. Because I don't know about you, but I'm much more comfortable with my laptop than with somebody else's laptop. We'll have laptops available, but bring your own if you want to. When I was a biochemist, we used to say that a biochemist would rather use his colleague's toothbrush than his colleague's assay, and now I think you can probably say the same thing for a laptop. I'd rather use my own laptop. So here's the underlying assumption. We're going to look at some other cases where we're also using fluorescence as a proxy for biomass, and we'll look at some data in the ocean that's almost real time, some of it. So the question is, did they grow? So did you get, you didn't plot everybody's data. Here I plotted the first 6 groups, and I stopped plotting them because it was getting pretty messy. Hey, look at this. Looks like you all pretty good in diluting. Here's day 0 when you added your, 50 mils? They're all pretty darn close. Day 2, notice it's not anything I would write home about in terms of an increase in biomass, although there is a little bit of a spread. So there's a lag. And a lot of times what microbiologists talk about is an S-shaped curve. So there's a lag, and then an exponential phase, and then a stationary phase. So that it looks kind of like, let's see if this pen has any ink in it. Because people don't put the lids on. Now there's nothing left on this in terms of the... Okay, I have to hold it exactly right. So if this is time, and this is biomass, you see something that looks like this. So this is called the lag phase, the exponential phase, the stationary phase, and then often you'll see a decline as the cells run out of something. And when we look at the growth rate, this is where you want it from, that exponential phase. And so if you look at the data that you generated, and I'm going to say you did a really good job, is here's the lag. Let's just look at the orange ones. That's group 6. How much did you add? 5 micromolar. So there is about half a micromolar to start. So we'll take that one because it has one of the higher concentrations. So you get that lag, then you get what looks like the exponential. And then look, it goes down. It doesn't stay at the stationary. Here's group 2. Yours went down. Here's group 3. Didn't change too much. Group 5, you did go down. The first one went down. So one of the really interesting things is that comparing to 2 years ago when I taught the class, the biomass never reached the same level. We went up to about 750 last time, and they didn't drop off that fast. So I have 2 questions from this. One of them is, why did the biomass, when the only thing limiting is phosphate, and 5 micromolar is not limiting, why did the biomass stop? And why did the culture start dying? So one hypothesis is that these are not truly azenic cultures, that maybe there's viruses in there. The other one is, maybe by having that lid, even though you cracked it, maybe there's not enough CO2 getting in there, and so they actually become carbon dioxide limited. But if that were true, I think you would see all the cultures go to the same high level and then crash. The other thing is, do you remember the media where it was a little cloudy? So maybe something else precipitated that's limiting. I used to grow cells with water that I collected off the dock at the Darling Center, and then I started having trouble having things grow. And Bill Mook, who is an aquaculturist up the river, he grows phytoplankton because he spawns his oyster larvae, and you have to feed the oyster larvae phytoplankton. And so he was having trouble with some of his cultures. So then I said, okay, I'm going to ask the Irish sea captain when he goes out past the mouth of the Damariscotta to get seawater for me. And so this is off the mouth of the Damariscotta. It's about 3 or 4 miles out. So is it the seawater? Is it something's precipitated from the autoclaving, or is there a virus in there? I don't know. Maybe when Dr. Karp-Boss comes back and she'll take the class over next year, I'll say, Lee, there's a problem. Need to get an undergraduate working on this to try to figure out what's going on. And I'll show you another difference, some data from 2 years ago. So this is great, but there's some puzzles in terms of what happens at the end that I really do not understand. Okay, let's look at some more data. So again, remember that we've got what they call the mother cell. It divides in two, so you have 2 daughters. And the reason that we calculate the growth rate as doublings per day, we do it log base 2. Remember when we were doing spectrophotometer? The reason that we converted it to log base 10 as opposed to, who's the physical oceanographers in here, the physical track? Okay, so when you work with stuff in the ocean, you're usually in the natural, the log E. Chemists work in log 10 because it's easier to look at a decadal scale and say, this is twice as big as that, as opposed to looking at the log base E scale. Well, if you're a phycologist and you're growing things, you work in log base 2, because when something doubles, if it doubles once per day, that's your slope for the number of cells versus time. So let's look at this. So here's the number of cells. You measured fluorescence instead of cells because we don't have a Coulter counter up here to count particles. And what you saw was something that looked like this, and then it crashed. And it looked like their different cultures had different rates of increase. So if you take log base 2, plot log base 2 versus time, m, the slope, is your doubling, because it's log base 2, it's doublings per day. And so the growth rate, if you were working with E. coli, your doubling time would be 20 minutes. And so your growth rate would be something like 90 doublings per day. Phytoplankton grows slower than that. And 2 years ago, the doubling rate was 1 per day, meaning the cells divided once per day. Now, everybody thinks science is cut and dried. You know, there's no room for decision making. If you did your homework right, what you'll see is that there was lots of room for decision making. So here's group 1, and this is log 2 fluorescence in relative fluorescence units versus time. And group 1 was the one that you didn't add any phosphates, so the ambient concentration was about 0.4, 0.5 micromolar. And so here I went ahead and I did the regression line, and here's the line going through the data. Are you impressed? That's a pretty bad fit, right? But remember, we had a lag and the cells didn't grow. So is it sensible to use the data from day 0 to try to calculate the growth rate? No. The cells plateaued, and in fact, toward the end, even some of them died. So is it sensible, if you're doing the growth rate, to use the last data set? No. So what I did is I picked day 1, 2, 3, and 4, and one could say, maybe should I have even cut that out? I think some of your other data are clearer in terms of more data points, but if I now take that regression, my slope, which is the growth rate, is 0.41. And so this is where the decision making came into play. Is I said it's not sensible to include this because there was a lag, and it's not sensible to include this. Did some other people see that lag and then the plateau? And so the trick and the art, it's really an arts and sciences, is figuring out, which ones, and if I kept, throwing out data points and I still kept getting that same growth rate, then that would give me more confidence. And I think with some of your data sets, you probably had like 6 good data points where it really looked truly linear. So then what I did is I pulled out all of the doublings per day. And group 9, are you 0? Was group 9 no addition?
Yes. Yeah.
No.
We ended up not being able to use our data because it was all
The phosphate, but yeah, the fluorescence data were good. The phosphate data, because we were having all that trouble with the spectrophotometer. But the thing that I don't like is in terms of, and I can show you graphically, so group 1 and 9 should have been replicates, but that's a pretty big difference in the growth rate, so is it light? The other thing is look at the growth rate. So these are, probably the higher growth rates, about 0.7, 0.75. And these are the highest concentrations, but here's an addition of group 10. What did you add? Is it 1 micromolar?
Yeah, because we had 2, so we had 1.
Right, so you're as high as the highest ones. So some of the questions, you can probably not see this because of these crappy pens, is do nutrients control the growth rate? I don't think we really see that in this data. There's a lot of scatter. And part of the reason we may not be able to answer that is if this is nutrient concentration and this is growth rate, you have a hyperbolic curve, and it may be for phosphate. Actually, why do I say maybe? I know this. I did my PhD on phosphate many, many years ago, is that this value where you go from limiting to non-limiting is about 0.2 micromolar. So even with our lowest concentration, I think we're not in the truly limiting range for this species. So here's a puzzle. Here's 2 years ago. What strikes you about the numbers for the growth rate? They're higher. They're a lot higher. And this is no addition. This is no addition. And that's closer in terms of replication. But this is an addition of 1 micromolar. And so there's a lot less variability as well. So I'm scratching my head. Why are the growth rates so much lower? So you're diploid. You know that. Most phytoplankton are haploid. Diatoms are diploid. And you remember what I tried to draw, I'm going to try to draw Thalassiocyra. Here's the girdle. So there's what's called an epitheca and a hypotheca. So the theca is the diatom frustrule. And so this is slightly larger than that one. And so this is a hypothesis. So I'm trying to figure out why they're so different. When the cells divide, this one stays the same. And it stays, this goes into that. Here, the hypotheca becomes the epitheca. So what do you think would happen if this happens many, many times in terms of the cell size? It gets smaller. And that's called the McDonald diminution in cell size. And do you know I'm going to pronounce it wrong, the von Bertolli hypothesis that I think it's an exponent of 3/4, that the larger the organism, the slower the growth rate? It's opposite for diatoms when they're going through this. The smaller the phytoplankton, as the population is getting smaller, the slower the growth rate. And then they go through something called oxospore formation, which is sexual. And so there's actually no exchange of genetic material when they're just dividing vegetatively, but they form an oxospore, and the oxospore looks something like this, and there's all kinds of different shapes and sizes. When it divides, it goes back to the original size, and so it gets bigger again, and it sort of resets that diminution. So anyway, here's another hypothesis, is that maybe these are in the small stage compared to these, or maybe there's some other reason that we haven't come up with. So anyway, this is really very surprising and puzzling. And if anybody else has a good hypothesis, so I'm going to hand this off to Dr. Karp-Boss and see if she can solve the problem when she gets back from sabbatical. The other point I want to make, do you remember I showed you this slide way in the beginning? You know, that people measure growth rates. Like a really hot topic right now is how are organisms responding to pH in a changing ocean? Okay, so you look at these. These are data points. Notice that there are error bars. What is error? If there's an error bar, did they do it once? Just a second. If there's an error bar, did you do it once? So they had to have done more than one experiment, probably something on the order of 3 or 4. So you did one measurement. So next time you look at a curve like this that has all these data points, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 times maybe 3 experiments. There's probably 33 of these. Next time you look at a curve like this, I think you'll have a little more appreciation of all the work that went in to generate it. And you know, what you did was contributing to one data point, because you take that growth rate, that doublings per day, that's what that is. That's the doubling per day, although they're using it as a slightly different formulation. Yes?
Oh, I was just wondering if we have the same experiment, or is it just 2 years ago and this year?
The year before that, everything died. And I didn't go back further, but no, actually, I looked at, I think 2011, the growth rates were high too. Mm-hmm. This is the first time that I've ever seen anything grow that slowly. So, and the reason I used to like it, I used to like the Lasiosira, is because it doesn't clump and it doesn't sink because it's little. Okay, fluorescence versus initial phosphate concentration. Do nutrients control the final biomass? Are you impressed? Look at the R square. This is all day 8. I would expect it to be much more linear if we were really looking at the control. So to me, you know, there's a lot more scatter. Some of the previous years we had better data, but I don't know if this is because things were kind of flaky in terms of their growth. But I think we can, if we look at a single culture, I think we can ask that. So this is what you should have for each of your cultures with, here's fluorescence with time. This is group 7. Where's group 7? You guys here? Group 7. Okay, so it grew pretty nicely. The initial phosphate was around 6, and so you can see that there's a decrease. You don't see it as dramatically because if the way that I plotted it was 0, if I plotted it and expanded the scale, you can see much more of a drawdown. But instead, what I did was I plotted here the phosphate consumed. So this is the phosphate consumed on day X relative to the initial concentration. And this is really beautiful. So this is showing the growth rate. And if you look at the phosphate that has disappeared from being inorganic in the media, and it's now part of the cell, DNA, ATP, they follow exactly the same pattern, which is really fantastic. And if you plot biomass versus the phosphate consumed, you can see that there's a 1-to-1 relationship. And so, and I looked at most of the data, and most of them show this relationship. So in terms of asking, is there a correlation between nutrients and biomass? If we look within an experiment rather than across experiments, we can see that there's a really good relationship, which I think you did great. I mean, this is real data. But I think this shows, this is the cartoon version back from a couple of lectures ago, this relationship between phytoplankton biomass and the nutrient concentration in water. And the reason that people are interested in that, and in terms of the prediction for using the Redfield ratio, is that if you know something about the N to P to C relationship, you can make some predictions. You saw this earlier. You know, here's data from a whole bunch of different sources. Chlorophyll versus phosphorus, which is similar. You know, yours is not on a log scale. Yours is a linear scale. And so there's a really good relationship in terms of the upper level of biomass, and you did it in your experiment. And I think that's pretty good. I raced through this slide last time in terms of the global distribution of eutrophication-driven dead zones. So if we look at the relationship between oxygen and carbon, you know that photosynthesis goes in this direction, CO2 plus water give rise to organic carbon plus oxygen. So oxygen is evolved as part of photosynthesis. Well, respiration goes in this direction. So if more phytoplankton are produced at the surface, aren't grazed by zooplankton, they settle down to the bottom, microbes are going to use that organic carbon. They're going to consume oxygen, and you wind up with all these dead zones worldwide. Anybody here a fisheries biologist? Any fish people? So they used to say that the biggest threat in terms of world fisheries was overfishing, And now they're saying the biggest threat is actually eutrophication and these dead zones, because a lot of the larval fish and the baby fish spend a lot of time in the water. Look at the United States. Okay, Casco Bay, still pretty clean in Portland, and that's because there's not that many people. So it's directly related to people. But you look all along the U.S. East Coast and the Gulf Coast, and then there are a few places on the West Coast, and these are either totally anoxic or they're hypoxic, which means low, like 10% of what they should be, and they're either permanently or seasonally. So population number is going up, and I think these are underreported in South America and in Africa and in Asia. But you look at Europe and all these problems. So if you're looking for a career with more people going up, more nutrients going into the coastal zone, they're going to need more managers and people who can either do the science or can make the policy in terms of decision making. So here's Long Island Sound. Used to be pretty pristine, and now it's permanently anoxic and then seasonally anoxic in many places. So how would you actually monitor? So next week we'll look at some data from the open ocean, but here's some data from Elkhorn Slough. There's a guy named Ken Johnson who's a really creative chemical oceanographer at Mombari. And he's a sensor developer as well as a chemical oceanographer. And the Monterey Bay Monterey Bay Research Aquarium is located pretty close to Elkhorn Slough. And this is near Castroville. Anybody here eat artichokes? That's the, Castroville is the artichoke capital of the United States. Really, really rich slough in terms of seabirds, in terms of marine life. But it's also a place where, really close to the slough, they grow strawberries. And so farmers' insurance is there's a relationship for phytoplankton between nutrients and biomass. Guess what? Same thing for crops. And so farmers' insurance is you add more nutrients to make sure that you're not going to have nutrient limitation to be limiting your crop. So the strawberry fields around here are just loaded with nitrate. You add a lot of nitrate, you're going to get phytoplankton. You have a lot of phytoplankton that don't get consumed. You can lose your oxygen. And how does that affect the food web? So Ken Johnson is developed this instrument, which I mentioned briefly early on. It's a spectrophotometer that measures in the UV, and it allows you to measure nitrate concentration without any chemicals. So you've all been measuring phosphate with chemicals. How cool would it be if you could measure a nutrient without doing any chemistry? You do optics instead. And so here's the sensing part of this instrument. So this is the data logger and the battery pack and everything. And so here's absorbance, just like you measure with the Carey spectrophotometer versus wavelength, only it absorbs down around 220. Dr. Damian Brady down at the Darling Center has bought a half dozen of these, and he's got one right off the dock, and then he's got two at the mouth of the Damariscotta. And I think, I don't know if it's one of you, but he's got an intern this summer looking at trying to interpret the data, because guess what? Nothing is ever simple. You want it simple? Go be a baker. So here's the nitrate absorption, but guess what? Bromide also absorbs down there, so you have to measure salinity, because bromide is conservative with sodium chloride. So you can get rid of that. And then in the river, we've got a lot of dissolved organic material, which also absorbs down there. So this intern, whoever he or she may be, is going to have one heck of a time this summer trying to figure out how to get the nitrate out. I mean, it's possible. They might succeed, or it might take 2 years to succeed. But But anyway, using this either a SUNA or an ISIS, you can measure nitrate. So here's Monterey Bay, Strawberry Road. That tells you something. So here's the slough, and it's surrounded by fields. And they put it on something called a LOBO. So it's telemetering data, and it actually uses a cell phone to send data back. And so one of the things that they were looking at, so here's salinity. They're getting a lot of water coming straight from the ocean. And then they have these two big rain events. Here's nitrate. So you remember from your Redfield ratio how much carbon you can get out of about 10 micromolar nitrate. This is mostly ocean water. And you see that it's pretty low and pretty stable. And then guess what happens when you have a rain event? Right, you got all the strawberry fields, you got all the nitrate. So it goes up to 200. Now, if you do your Redfield ratio calculation, how much phytoplankton can that support? And so the strawberry people were actually really interested. You would think that maybe they wouldn't be, but they were actually pretty excited about having these moorings deployed that would tell them something about this is money washing down as well as causing problems for the environment. Because if you over fertilize and it just gets washed out, you've just wasted your money. But there's the strawberry fields. And so the lesson, sort of the main point that I'd like to have you leave with is you had a successful experiment. If you look at experiment to experiment, if you look within an experiment, what you should see, and I think most of you probably saw it, is a really close correlation between the phosphate that was consumed and the biomass that was produced. And if that's the lesson that you take out of that experiment, I think it was pretty good. I think it was a success. And so I will see you in class at your appointed time.